Alright, welcome y'all to an AP Chemistry review video. I'm going to go over the Unit 8 test, and I have written here the most commonly missed questions, 1, 2, 4, 5, 6, 8, 9, 12A, 12B, 13A, 13B, and 14B. So let's go over those in review. So the first one relates back to topic 8.1, and it says a value of Kw at 37 degrees, and it gives us a value and says, which of the statements about pH and pOH are true? So we know that at a higher temperature that water is going to ionize more, right? Those H2O molecules are going to turn into H3O plus and OH minus a little more often than they would at 25 degrees. So, but however much they ionize, any hydrogen that's lost by water is going to be given to another water molecule. So this ratio is going to stay 1-to-1. So we know that therefore the concentrations will be the same. So we know that pH and pOH must be the same because they're the negative log of the concentration of H3O and O3O plus. So it can't be A, it can't be B. It has to be one of these. So now we're just left to figure out, well, would the pH be equal to 7 or would it be less than 7? Well, we know that 7 pH for water is only true at 25 degrees. So what's going to happen at a higher temperature? Well, higher temp means that these are going to dissociate more. So there's going to be a higher K for water dissociating, which remember, water has its own special equilibrium. It's Kw. So what about the pKa? That's going to be a lower number. It's going to be less than 7. It will not add up to 14. Remember, so pKw is the negative log of Kw, which in this case will be less than 7. It'll be because so what I'm trying to say here is the higher the Ka, the lower the pKw. And then when you divide pKw in half, you get less than 7. So the pOH and pH is going to be less than 7. Best answer would be C on that. 8. So the next most commonly missed question was number 2. Number 2 goes back to 8.2, pH of strong acids and strong bases. I think what most people got mixed up on here is that when BaOH2 dissociates, it's going to dissociate into a barium molecule and then 2 OH minus molecules. So you have to take that into account. So if you're trying to find the pH, well, first you need to find the pOH because we have a base here. It is a strong base, so you can just directly put the concentration in. You could just say pOH equals negative log of hydroxide ion concentration. And then whatever you get for pOH, well, okay, just remember you're going to have to multiply that times 2. It's going to have to be 2 times whatever the starting concentration. This 0.1 was going to have to be doubled. So 2 times 0.1 is 0.2, okay? So it's a negative log. So remember how to get pH? pH is 14. If you add pH plus pOH, you get 14. So if you want to find pH, you have to take 14 minus pOH. And since we're subtracting, and this is a negative log, 2 negatives make a positive. So pH equals 14 minus a negative pOH, so plus the log of 0.2. I think this part right here is probably what messed most people up, but should be D. Number 4 is the next question we're going to go to. So 4 dealt with 8.3, topic 8.3, weak acids and weak bases. And we're given a table and we're asked, well, which one would require the most moles of NaOH to neutralize it completely? So a few key things to recognize here. All have the same molarity. So that doesn't really tell us a whole lot. So then generally we would look at the lowest pH. That's some helpful information. These all have low pHs. Sample 1, sample 2, and sample 4. They're all low pHs, okay? So let's start wheeling and dealing here. The only thing that we really see that's significantly different is the volume. So like if I'm trying to compare 5 milliliters of 2.3 pH acid, well, that's a higher pH than the first one, and it's a lower volume. So like this one, like we automatically can tell that it's not that one. Okay. And this one had the higher pH. So it's not very acidic. We can automatically rule that one out. So it's down to these last two. This one is more acidic, so it does have a higher hydrogen concentration. But if we're titrating it with NaOH, these are both eventually, all the moles of acid are going to end up reacting eventually, because NaOH is a strong base. If there's any acid in these, it's going to react with that NaOH eventually. So when we compare these two, there's more volume in sample 4. So all things considered, the one that has the more volume has more moles of acid, okay? Because you're multiplying the concentration times a larger number, so you would get like a higher number of moles of acid. So even though it doesn't quite have the pH, pack the same pH that the stronger acid does, it has more volume. That's what really matters in the case where when you're titrating NaOH. So best answer there is going to be D. All right, moving on. I think the next question was number 5 that was also commonly missed. So we have a titration curve, and we're asked which of the following would be a best estimate for PKB and KB. So what we are going to do here is we are going to look at this area, the buffer zone, okay? And then right in the middle of the buffer zone, we have this special place. Why are we looking at the buffer zone? Well, this is a weak base, okay? And it's being titrated with a strong acid. So when you have a weak and a strong combined, that creates a buffer solution. So if we look at this buffer solution, it's going to reach the half equivalence point, right, where the moles of weak acid equal the moles of weak base, right in the middle of this line, which is about 11, okay? About a pH of about 11. Now, what do we know about the half equivalence point? A good thing to remember is that at the half equivalence point, pH is going to be equal to pKa, or about equal, pretty close. All right, so if pH is that, okay, we're asked for pKb. So how do we get there? Well, recall that pKa plus pKb is going to equal, am I saying this right? Hang on. Let me think about this for a second. Yeah. pKa plus pK will be 14. Okay. So assuming, standard conditions, and we are given standard conditions at 25. All right, so if the pH is equal to the pKa, then this number must be 11. So we have 11 plus pKb equals 14. Okay, well, you do the math on that. pKb is 3. Okay. And then how do we get from that to the Kb? Well, pKb is the negative log of Kb. So we have to do some math here But basically, we can see that if it's 3, then it should be 1 times 10 to the negative 3, because of just the fact that it's just a whole number. But the other way that you could do that is 10 to the negative pkb. And then you would get the same number. Okay, so... Oh, wait, did I say... Yeah, that's right. Okay, so A. 5 is 8.5. Acid and base titrations, if you're wondering about that. Okay, now we're moving on to number 6. Remember, I started these, so I wouldn't need to look. All right, so we're looking at and we're basically said, what's the largest value for Kb? So a high Kb is going to be a strong base, right? It goes to products more. So the numerator is higher than the denominator. Okay, we learned in 8.6 that a strong base, how do we tell that? Well, it has a weak conjugate acid. It's the same thing as a weak conjugate acid, because if something's a really weak conjugate acid, it's not going to lose hydrogens very easily. So strong bases do not lose hydrogens. If anything, they accept them. So it's like saying the same thing. If something's strong on one side, then its conjugate is going to be weak because of the reciprocal relationship there. So how do we find weak conjugate acid? We learned in 8.6 that when you have a hydrogen and we don't want it to leave easily, that like basically more electronegative atoms near that hydrogen will make it more likely to leave. Will make the H more likely to leave. And why is that? Well, okay, let's think about this. We know polarity, right? So if we have Na and Cl, we know that sodium has 1 valence electron and the chlorine has 7, okay? And the chlorine is very electronegative, okay? Sodium is not electronegative at all, okay? So what happens? In this situation, we know that chlorine will steal that electron, okay? Well, it's really no different if you have a, it's not too much different if you think about an H and, let's say an H bonded to a nitrogen, bonded to a chloride. Okay, this chloride is very electronegative, okay? Now, why is this hydrogen here? So it can have a stable duet, okay? It can have 2 electrons in its outer shell, okay? So it has 1 electron. It's sharing 1 electron. But what's going to happen here with if you have a really electronegative atom over here? Well, the electrons are more attracted. This is a polar set of bonds, okay? So what's going to happen is these electrons are more pulled over to the chlorine. So with an atom as small as hydrogen, it's more likely, it's not going to happen every time because chlorine, this isn't an ionic bond like here, it's a covalent bond. But some proportion of these molecules are going to have enough energy. The chlorine's going to have enough electronegativity that this hydrogen is going to bounce up against something, and the electron is going to come over here to the chlorine, and it's going to allow that hydrogen to sort of pop off and be attracted to some base that's out there. So the more electronegative element that you have that's closer to hydrogen, as I was saying here, the more likely the H will leave, which would be a strong acid, okay? But what we want is the weakest acid. So let's just say which out of these would be a strongest conjugate acid. The This one has nitrogen and chlorine. This one has nitrogen and oxygen. This one has nitrogen and another nitrogen. So N, O, Cl, they're all very electronegative, okay? So these are all fairly strong acids. But carbon is less electronegative, okay? It's less electronegative. It's more to the left on the periodic table, so you know that. So these would be better conjugate acids. This would be a weaker conjugate acid. So this, therefore, would be the strongest base. And that's the best in-depth way I could think of explaining, or that I would use to explain that. So the answer would be A on that one. Okay, let's move on to number 8. What we have here is a weak acid and a weak base. Okay? And they're equimolar. So when you have those two recipes, equimolar amounts of weak acid and weak base, that tells us we have what? Well, 8 is covering topic 8.8, properties of buffers. So we have a buffer on our hands. So what does a buffer do? Okay, it resists changes in pH. How does it do that? By having equal amounts of weak acid and weak base to react with acid or base that's added to the solution. If you throw some base in there, weak acid's like, I'm going to go clean that up. And the weak base is in there, the weak base is like, and you throw some acid in, the weak base is like, I can clean this up, no worries. So what we're looking for here are two equations where we're adding OH minus and it's reacting with the weak acid. Or we have the weak base and it is reacting with hydronium, H3O+. So let's look for that. Really, well, okay, I'll just tell you, D, right? You have a weak acid that's reacting with hydroxide to form water, neutralize it. And then it leaves some base, but it's a weak base, so we don't care about it. In this situation, we have hydronium acid. It's reacting with that weak base, F-, and it's just forming HF and H2O, and that's it. All right, so moving on to number 9. This is just a straight up good old-fashioned 8.9 Henderson-Hasselbalch equation problem, okay? So, you write down your formula, pH equals pKa plus log of A- over HA. And you start plugging and chugging, right? You've got 100 milliliters of tin here, and then 100 milliliters of 0.2 moles. So you're going to have to, find the number of moles. 0.1 times 0.02 here. Or times 0.2, I mean. And that gives you 0.02. And then, same thing here. You get, 0.01 moles. Okay, so then you start plugging those in. The other thing that we can see is that the pKa is 4.8. So we're just going to start plugging stuff in. We got 4.8 plus log. And then our, let's see here, base. Our base has a molarity of 0.01 or concentration of 0.01. Oh, I should have added that you would have to combine these to get the total volume. And then, so there's a little more math than what I'm actually showing here. But then 0.02 goes on the bottom, and then you take the log of that and all of it, and just, do the math, and then you end up with a pH of about 4.5. pH of about 1.5. Right. Let's move on to the FRQ. Okay, so 12A wasn't too hard, and I wouldn't say a huge amount of people miss this one, but if you did, it's for a reason that is very easy to fix. So how do you figure out which one's the titrant, which one's the analyte? So the analyte is what is the unknown, okay? Titrant is known. So if you think back to our titration lab, this is the unknown. It's sitting in a Erlenmeyer flask, okay? And we're adding drops of something we do know until it neutralizes it and we get that nice color change, okay? So this is our known. So this pH meter here, what we're talking about here is this unknown, okay? We're analyzing the unknown. And that's the whole point of graphing this is that we're taking something unknown and we're doing a titration so that now we know something about it. So when you think about this, you just look and you'd say, okay, well, pH of 1, okay? It started out with a pH of 1. This is an acid. This is an acid, y'all. And then it becomes easy. The HCl is the acid. All right, going on to E, what is the difference between equivalence point of a titration and end point of a titration? So equivalence point, almost everybody got that. I didn't have to count that off too much. That's where it's pretty straightforward. The moles of acid equal the moles of base. Okay, you have added exactly enough the same amount of moles of base or acid or vice versa to your acid, so that they have reached an equivalence point. They've reached a neutral pH, and that's how you know what the concentration of this unknown acid is. So what is the end point? Okay, this is where the color change happens. So the idea behind this is that, like, you know, there's only a certain number of color chemicals out there that are actually going to change color at one specific pH, and then it's usually a range. Like it's just very difficult to get something that's going to change colors at exactly a pH. So what we do is we just remember how you titrated? You got just not like pink. You just wanted like a little bit of pink, just a tiny bit of pink. So it's usually just past the equivalence point. Okay, so we select some kind of chemical that's going to change colors just a little bit past the equivalence point so that we know that it happened, right? Because we see a color change, but it's just a tiny little bit of a color change. So then we just try to make that pH as close to actually where the equivalence point would be as possible. We try to close that gap, get it as small as possible. But this is if you're asked this question on the AP test, make sure you talk about that, like it's where the color change happens, okay? All right, moving on. This one, it was a lot, and I think people just got tripped up on the same things for this. So let's just go through. Basically what you wanted to do is look at each of these, identify the species, and then from that I get a good sense of what the pH would be. So let's just start with the first one. We have NaOH, that's a strong base, and then HBr, that's a strong acid, okay? And we have equivalent amounts of everything. So we have equimolar amounts. So if we combine these, like in a titration situation, this would be like the same thing as the equivalence point. So the pH is going to be 7, right? We know that. We know that with just this information that we have. All right, solution Y. Again, we see the strong acid making an appearance, HBr, but NABR. This is what tripped a lot of people up, and this is the AP test being tricksy with you. Okay, NABR is just a salt, okay? So a salt is not a base. or an acid. Okay, so be careful with that. If you see a cation and an anion together and there's nothing here that's either going to donate or accept a proton, like Br minus is not, it's not going to accept hydrogens. How do we know that? Well, because HBr dissociates 100%, okay? If Br would accept protons, then HBr would not be an acid, a strong acid. It would be a weak acid. But since it's a strong acid, strong acids do not have conjugate bases, okay? So this is nothing. This is just a salt, okay? When the conjugate is a strong acid, strong base, okay? So really all we just have is a strong acid. So this pH is going to be low, right? pH of about like 1 to 3 or something like that. Okay, so then we have the last one. It's a weak acid and it's conjugate base. Okay, so how do we know this is a weak acid? Well, because it's not a strong acid. There's just too many atoms in this formula for it to be part of that crew. So weak acid, conjugate base, and again we have equimolar amounts. So what is that? That is a buffer, okay? And since they're equimolar, pH is going to be about the same as pKa. So if we take this number and take the negative log of it, then we get the pKa. pKa equals negative log of Ka. So if you do that with this, you would get that pKa is about 4-ish. It's about 4.76. So the pH has to be about 4.76. All right. So then when we work it out like this, we've got pH 7, 1 to 3, and then 4.67. Okay. So the one with the highest pH is going to be that first one, neutral. And then the middle one is going to be Z. It's a little more acidic than that. And then the lowest pH is going to be that Y in the middle. This is the most common thing. Like by far the most common error. But another error was that people did not say or explain that this is a buffer solution here. So that's what mixed people up, either failing to recognize that this is a buffer solution and that since it's equimolar, the pH should be equal to pKa, and then just like realizing that a strong acid does not have a conjugate. Okay. B was not missed a huge amount, but it was missed enough that I'm going to go over it. Does the pH increase, decrease, or stay the same? Remember, pH is the negative log of H3O+, okay? So for Y, we're talking about an acid. So what if we add water? Well, if you add water, the molarity is going to do what? It's going to decrease, okay? So this is the negative log. So what if the molarity decreases, then the acid gets weaker, okay? So remember, pH is always going to do the opposite because of this negative number in between the two. pH will do the opposite of H3O+. So the acid gets weaker and the pH increases, right? It gets closer to water, closer to 7.0. So I saw a lot of students talking about water as like a base or an acid in this case. Water is just adding more water. How do I put this? Like the dissociation that happens is only going to happen because of the strong acid. So the only thing that really matters here in terms of H3O+ concentration is how many moles of the strong acid concentration. Like there's more water, so there is more auto-ionization of water. Like I get that, like, but it's not significant enough. It would, what's the auto-ionization of water? 1 × 10⁻14. That's like almost nothing. Okay, it's just not happening enough that it would actually make the pH stronger. The thing driving this is that the acid became more diluted. Okay, last question. This one's kind of a little bit of a doozy here. This is the one where you have to do some, where those ice tables come in handy. So you're trying to find the Ka for propanoic acid, okay? So, let me just flick back to my notes where I did that. This is 14B. 14B. Where'd you go, 14B? Right here. All right, here we go. All right, so you're asked to find the Ka. I'm going to work down here. Ka is concentration of products over concentration of reactants. Always, always. Right? And what's the reaction for acid? Well, he gave it to us right here. So we're just going to plug in those products that are aqueous and put this in the reactants on the bottom because it's aqueous, and ignore that H2O because it's a liquid. So we get that Ka is going to be equal to the concentration of CH3CH2COO minus times the concentration of H3O plus divided by the concentration of the original acid CH3CH2COOH at equilibrium. All right, so now we put ourselves to the work of figuring out what numbers would be plugged in here and how we would do all that. So I'm just, to avoid writing all this down, I'm just going to abbreviate propanoic acid reacting with water, H2O, is going to yield me propanoic base plus H3O plus. Okay, our starting concentration, we're told, is 0. 0.2. Were we told that specifically? Where did I get that number from? Oh. I think I got it from this. Yeah, that's what I did. So I use the pH. pH equals the negative log of, or did I? No. I just took these two and, yeah. I just used those and then worked out. Wait, is that? Oh my gosh, my brains are getting all scrambled here. Oh, okay. Okay, so it's this 2.79. If you're trying to find the concentration of something, you're gonna say, well, okay, H3O plus, since we know what the concentration, the H3O plus is the negative log of pH. Okay, so we take the negative log of pH, so we have to undo this, right? Or what am I doing? Okay, let me back up here. Okay, so pH equals negative log of H3O plus. The pH is 2.79. So how do we figure out the concentration? We have to do the negative anti-log, okay? So how do we do anti-log? If we're doing the opposite of this to get the concentration from the pH, we're going to go 10 to the negative pH. So 10 to the negative 2.79. And that's going to give us 1.6 times 10 to the negative 3. Okay, that's our concentration. Getting a little ahead of myself here. So we're going to lose some propanoic acid. We started out with no propanoic base, its conjugate base, and no hydronium. But we gain those two things in equal proportions since they both have a coefficient of 1. So we end up with 0.2 minus x, and then x, and then x. So what's our equilibrium expression become? Well, we just plug our values in here. It's x squared over 0.2 minus x. We know from this information that the x is going to be negligible, so it's just 0.2 equals x squared, and that is equal to what? Well, we just found what the concentration of H3O plus should be. Okay, so what we're going to do is we're going to plug that into this equation because H3O plus is x. They're the same thing, okay? So we'd have to go 1.6 times 10 to the negative 3 squared divided by 0.2 gives us the Ka of the acid, okay? And then you plug the information in and you get that it should be 1.3 times 10 to the negative 5 with the, correct number of sig figs. So that's how you find Ka. Okay, oh my gosh, this is a super long video. I hope this is helpful for you. By the way, this is 8.3. Properties of weak acids and weak bases. This question, oh my golly, it draws from like 2 or 3 different units. I couldn't really just point to one specific unit for that one. And then this is titration, 8.5 here. And then equivalence and endpoint, that was 8.7. That's one of the ones I asked you to do over the spring break. All right, scholars, good luck. Good luck to you, okay? Hang in there. You guys are doing great, and just keep up with it. All right, bye-bye.